Hello everyone, I hope you're doing well. So in this video, we're going to discuss the first 5 problems of Codeforces Round 881, which was rated for Division 3. So this contest was probably like a simple contest in terms of the recent Division 3 rounds. So the last round I remember was not very simple, but the problems A to E were not very difficult. Only the last 2 problems had something in it. I was not able to solve F1 and we're just going to discuss the first 5 problems. So let us quickly start with the first problem. So this particular problem is Sasha and coloring. Now they say that we can color the elements in any color and any number of colors we can pick, right? So like you can see there are 5 elements here and we can color them in any manner. So what we have to do is for each of the colorings, for example, red is a color here, we have to take the maximum element and we have to take the minimum element and subtract them, right? So the value that we get after subtracting them is called the cost of that color, right? So we have to find this cost among all the colors and we have to find the maximum value of such cost. So basically, let me just show you this particular thing with the help of some examples. So I'll take this one here. So you see, I have this value, and if I write the elements in order 1 and then I have 3, then I have 4, then I have 5 and then I have 6. So I can color these elements in any colors, right? And the value that I get from each of the colors has to be maximized. So for example, if I color this particular 1 and this particular 6 together, so the total value contributed by them will be 6 minus 1, that is equals to 5, right? Now I choose another color and I color this element and this element. So the total value contributed by them will be 5 minus 3 and that is going to be 2, right? And if I choose the middle element, so it is alone. So I have to choose a different color, right? So if I choose light blue for this, then this 4 minus 4 will be 0, right? So the maximum answer that we can form in this particular case is 7, right? So this would be the most optimal way to form the colors. Why? Because I can take the first element, that is the smallest element, and I can take the largest element and find the difference. So in any array, if I take the maximum and the smallest element, their difference would be the maximum difference that I can form from the array, right? So I am taking these two elements and coloring them in some color, right? So I am taking the next two elements, the next smallest and the next biggest element, and coloring them with the same color, right? So this way I can always maximize my answer, right? So basically I just have to, like for example, if there are 3 colors, 1 color, 2 colors, 3 color, I have to maximize the value of S1, S2 and S3, and this is a valid way of maximizing this whole value. So let me just show you my summation and how I did it. So you can see I've created a vector V of size n and I have taken input in it and I've sorted the vector. So I initialize my answer with 0 and I initialize 2 variables I and j. I is initialized with 0 and j with -1. So basically I'm setting 2 pointers, and while I is less than equals to j, I'm just adding this particular value to my answer. So V of j minus V of I, right? And I'm also decrementing j. So this post decrement, after this operation has been completed, then the value of j will decrement, and similarly I am doing post increment on I. So you can also write it as V of j minus V of I, and on the next line you can do plus plus I and minus minus j. Both of these are the same thing. It's just that I'm moving the I pointer forward and moving the j pointer backwards, right? And now I can just directly print my answer. So this would be the solution for the first problem. Now let us have a look at this second problem. So the problem statement is pretty big, but all they want to say is that we have been given an array of length n. It can consist of any values. Some values are positive, some values are negative, and in one operation we can choose any subsegment and multiply it by -1, right? So we have to tell the minimum number of moves to make the sum of the elements in the array maximum, right? So we have to print the maximum sum as well as the minimum number of moves. So let us take an example from here, and let us take the second example because it also has zeros. So if I have these values here, so obviously there is one very obvious thing in this particular question, that if I want to maximize my total sum, if I have these values, I would always want to take the absolute value of all the values present in my array. So the maximum value that I can form in this case is 3, 4, 5, 6 and 7, right? So 7 is the maximum value that I can form in this particular case. Now there will be no other maximum value. This will be the maximum value in any array. I'm just taking the absolute value of all the values present in the original array. Now, how do I actually form it? So, for example, if there are some negative values, I want to convert them into positive values, right? So, there is one way that I find all subsegments of negative values. For example, -1 is there, then 1 is there, then -2, -3, then some positive number 10, then -1, right? So, I can select this subsegment and then this subsegment and then this subsegment and multiply them individually by -1. So, what will happen is this will become positive and this will become positive and the others were already positive, right? So, this is one way of doing it. The other interesting way of doing this is I select the positive subsegments. So, what is the actual use of selecting these positive subsegments? You will realize that if I make one operation like this, if I choose the whole array and make an operation on it, then all the values will get inverted. So, all the positive values will become negative and all the negative values will become positive. So, those positive subsegments which were initially positive are now negative, right? So, I can choose these subsegments now and make them positive. So, there are two ways actually. Either you can take the negative subsegments, right? Count negative subsegments and that will be your answer, right? The other way will be 1 plus count positive subsegments, right? So, this one is because I want to apply the operation to the whole array such that all the subsegments will get reversed. All the positive will become negative, all the negative will become positive, right? So, I am just adding 1 to this particular case. Now, what happens with zeros, right? Zeros are a big trouble to us. So, zeros can be considered in both of the ways. They are neither positive, they are nor negative. So, what I did during the contest was I just completely ignored zeros. So, if I have an array like this, -1, 0, 0, -2, 1, 0, -3, 0, I created a new array like -1, -2, 1, -3, right? I created a new array like this. So, there might be other way of solving this as well, but I realized that 0 are not at all necessary and they can be counted in any positive or negative. So, why just not remove them, right? So, I created this vector first and then found my answer on this particular vector. So, let me just show you the code. So, you will see that what I have done is I have created a vector size n, right? So, this is v2. Now, I have created another vector v. So, I am copying all the elements from v2 into v only if I is non-zero. So, if I will be true when I is non-zero, right? Now, if the vector v, the new vector v has some size, that means all the values are not 0. So, if all the values are 0, my v will not have any size and I can just go to this else part and print 0, 0. Otherwise, what I'll do is I'll count the number of negative subsegments and positive subsegments. So, the way I'm doing this is initially if the 0th element is negative, I just initialize negative with 1. Otherwise, I initialize positive with 1, right? So, this is a Boolean condition. It will return 1 if it is true. Otherwise, it will return 0. So, I initialize my answer with absolute of 0. So, this is actually going to store the sum, right? Now, for all the values from 1 to size of vector v, if v of I is greater than 0 and v of I is I minus 1 is greater than 0 and I am taking their not equal value. So, basically this is going to return true if v of I is greater than 0 and this is going to return true if v of I minus 1 is greater than 0. Now, if these two values are different, that means one is positive and one is negative, then only I come to this particular part. So, if the current value is positive, that means I have found a new subsegment which has positive values. So, I'll increment my positive variable. Otherwise, if v of I is negative, that means I have encountered a new subsegment which have negative values. So, I'll increment my negative, right? And I'll add the absolute value of v of I to my answer. And at the end, I can just print the maximum possible sum, that is the answer. And I'll print the minimum value of negative subsegments and positive subsegments plus 1. Whichever of them is the minimum, I'll print them. So, this would be the solution to the second problem. Now, coming on to the third problem. So, this is like a very simple problem. You will see that it is called sum in a binary tree, and basically we have been given an vertex. So, it can be any vertex, like for example 11, right? And we have to find the sum of all the elements which are in the path from 1 to 11, right? So, you will see the simple property of binary tree is that, so if I show you, if this is the node 1, this is node 1, this will be node 2 and this will be node 3, this will be node 4, this will be node 5, this will be node 6 and this will be node 7. So, if I am at any node, right, so if I am at x node, its left child will be at 2x and right child will be at 2x plus 1, right. So, if I am at node y, its parent will be at y by 2, right? For any child, even if it is the right child, its parent will be at y by 2. Even if it is the left child, its parent will be at y by 2, right? So if I'm at 7, its parent is 3, right? So I can calculate by 7 by 2 is equals to 3, and I can find 3's parent as 3 by 2 is equals to 1, right? So basically I just have to add all these values till I reach the root element. So what I can do is, let me just directly show you in the code. The code is not very difficult as well. So what I've done is, I've initialized my answer with 0, and while n is non-zero, right, I'll just add n to my answer and I'll just right shift n by 1. So right shifting means dividing n by 2. So if I divide n by 2, I'll move to its parent. So this is exactly what I want. I can just easily trace back my path from my last node n to my root node 1, right? So I can just add all of these values to my answer and I can just print my answer. So this was the third problem, and this was just a basic property of like the parent of a node, which you can easily calculate by doing n by 2, right? So now let us have a look at the fourth problem. So this was a pretty straightforward problem, and I'll tell you what the problem says. So let me just directly explain it here. So it says that there is a tree, right? So a tree can have any structure like this, right? Let's say this is a tree. Now the special property of this tree is, at exactly two nodes, there will be an apple, right? And what our character is doing is, there is some person, let's say the person P is shaking the tree, and once he shakes the tree, the apples will go to one of the children's, right? So if the apple is present at this particular node, it can move to this particular node or this node, right? If the apple is present at this node, it can move to this particular node, right? So eventually what will happen is, the apple will keep on going to the children, and once it reaches this particular leaf node, it will fall, right? So what we have to tell is, we just have to tell the number of pairs I and j which are the possible leaf nodes or apples of apples. So leaf node of apples means the last node at which the apple will be present. So for example, in this particular case, what can happen is, the apple is here, so it can go to this particular node after one time, and this can go to this particular node after one time. Let's say the apple ends here. Now this is after two shakes, and here also after one shake the apple will be here, and then the apple can be here, right? So this is one way of ij, right? This is I and this is j. Otherwise, what could have happened if the apple did not go here, the apple could have gone to this particular path and it would have landed here. So this would be another j, j2, right? So we just have to find all such pairs. So you can clearly see the answer to this problem will always depend on the number of leaf nodes we can visit from any particular node. Because for this node, I can go to this particular leaf node, this particular leaf node, this particular leaf node, right? So from this node, I have three options to go, three leaf nodes to go, right? Similarly, for this particular apple, I have three leaf nodes to go. So if both of them have three leaf nodes to go, the total number of combinations I and j will be 3 into 3. So this is exactly what I want to find. So my answer will be the total number of leaf nodes I can visit from either of them, and since these two like cases are independent of each other, my final answer will be the number of leaf nodes I can visit from the first apple, and then multiplied by the number of leaf nodes I can visit from the second apple, right? Now how do we actually calculate the number of leaf nodes we can visit from any node? So for this, you can just perform a simple DFS, and when you are at the leaf node, how do you identify a leaf node? So if it is a tree and you have made bidirectional edges, so the leaf node is always going to have a single edge, right, which is the incoming edge. But since it is a bidirectional node, so it will be present in this particular node as well as this particular node. So to identify a leaf node, you just have to check whether the number of nodes connected to it is equals to 1 or not. So you can easily see in this whole tree, only the leaf nodes will be the nodes which are connected to only one node. There is an exception to this particular case, and that is the root node itself, right? So the root node can also be connected to only one node. So you can just add a simple if condition for this particular case. Otherwise, you don't have to check anything else. You can just easily identify what is the leaf node by just checking if the number of nodes connected to it is equals to 1. Now you have found a leaf node, right? So let's say I have an answer variable which will store the number of leaf nodes I can visit from any node. So the answer for that particular last node, let's say x, will be equals to 1. And for all the other intermediate nodes, for example, from this particular node, I can visit G1, I can visit G2, I can visit G3. So these are the 3 nodes I can visit from my current node. So my answer of current node will be equals to answer of G1 plus answer of G2, answer of G3. So for the leaf nodes, the answer will be 1, and for all the other remaining nodes, the answer will be the summation of answer of all of its children, right? So let me just show you the code for this particular problem now. You will realize that this is very straightforward. So what I have done is I have created a integer n, and I have taken input in n, and I am initializing a vector, double dimensional vector g of size n. So this will be my tree, right? Now I take n minus 1 values and I decrement them by 1 just to take 0 based indexing. I push back y in x and I push back x in y. So I am creating a adjacency list. Now I create a vector of children, right? So this will essentially store the number of leaf nodes I can visit from any node, and I call my DFS function starting from 0. So if the size of my current node or the number of nodes that are connected to my current node is equals to 1 and the current node is not equal to 0, because if the current node is 0, that means it is the root node, right? So in this case, what I'll do is I'll set my children of node as 1, right? So the number of leaf nodes I can visit from the current node is 1, and I can just return from here. Otherwise, what I'll do is I'll visit all the children, and if the children is not equal to parent, if that particular child is not equal to parent, that means I can visit that child, and after visiting, when I come back, I'll add the value of the child to my current node, right? So this would be the whole part here. And now what I do is I just take the m inputs for all x and y, and I can just directly print answer as children of x minus 1 and multiply by children of y minus 1. So x minus 1 is just because of 0 based indexing. Similarly for y minus 1, I can multiply these values and get my answer. Then I can just directly print my answer value. So this would be the solution to the fourth problem. Now let us have a look at the fifth problem. So this was a simple yet decent problem. If you know binary search, you will be able to implement it. But if you don't know, then this with the help of this problem, you can easily learn a new technique. So basically, they're saying that we have been given some segments, and a segment is called beautiful when the number of ones in that particular segment is strictly greater than the number of zeros, right? So this is our whole criteria. Now we will be given some queries, right? So for each query, initially all the elements in the array are 0. Now for each query, what I have to do is I have to set that particular element as 1, right? If after setting that element as 1, at least one of the subsegments become a good subsegment or a beautiful subsegment, that means I have to print that particular index. So if it happens after the first query, I have to print 1. If it happens after the second query, I have to print 2, and so on. So let me just show you with the help of this example. So basically what is happening here is, let me just create an array. So the array here will be of size 5, right? Initially all the values are 0. So let's say this value is 0. So let's say this value is 0, this value is 0, 0, 0, 0, right? Now they have asked us to mark some subsegments. So the first subsegment is 1 to 2. So 1 to 2 is a subsegment. Then 4 to 5, 4 to 5 is a subsegment. Then 1 to 5, this whole is a subsegment. Then 1 to 3, 1 to 3 is a subsegment, and then 2 to 4. So 2, 3, 4, this is a subsegment. So if any of those subsegments become a beautiful subsegment, that means I have found my answer. Now the first index is 5. That means I have to change the element at index 5 to 1, right? So once I have changed this, now the next value is 3. So I have to change the value at index 3 to 1, right? Till now none of the subsegments have become a beautiful subsegment. Now I have to change the value at index 1. So this particular value becomes 1. So at this particular instance, 2 of the subsegments have now become beautiful. So the first subsegment is this one, because the total size is 3, right? And the total number of elements is 3. The number of ones are 2 and the number of zeros are 1. So the number of ones have strictly become greater than number of zeros. So this is a beautiful subsegment. So this has become beautiful. Now there is one more subsegment, this whole subsegment, because the number of ones are 3 and the number of zeros are 2. So this is also a beautiful subsegment, right? Now both of these are beautiful. So our answer will be 3, because at index 3 we got at least one beautiful subsegment. So how can we solve this particular problem? you will realize that this particular problem can be solved with binary search. So how do we solve this with binary search? Now in this particular problem, you will see that if I can form a beautiful subsegment at index 3, it will always be possible to form a beautiful subsegment at index 4, at index 5 and so on. So basically our truth array will look something like this. This will be initially false, that I have not found any answer, and after some index it will become true, right? So my task is to find this smallest true value, right? The smallest value at which I found at least one beautiful subsegment. So I'll use an invariance technique of binary search, in which I mark low point as -1, as this will never be true, and high point as q plus 1. So q is the number of inputs, q plus 1, as this point will always be true, right? I'm just considering it to be always true for now, right? So once I calculate my mid will be, I will assume that I am taking the first mid values from this input array, right? So let's say the mid value was 3. Let us consider 3. 3 is the answer in this case. So let us consider 3. So I see that index 5, 3 were unmarked. So I'll create an array. I'll mark index 5, 3 and 1. So this is 1, this is 3, this is 5. And I'll calculate its prefix sum. So once I calculate the prefix sum, it will look like this: 1, 1, and then 2, and then 3. Right. So what is the use of prefix sums here? Now what I can do is I can just traverse through all the subsequences. I know what is the value that I need. So if I want the number of ones to be strictly greater than the number of zeros, then let's say the this is the size of the subsequence. Then the value that I need is size by 2 plus 1, because I want them to be in majority, right? So this is the value that I need. With the help of prefix sums, I can easily calculate what is the number of ones in any subsegment. So if I want to find the number of ones in the subsegment L to R, then my answer will be prefix of R minus prefix of L minus 1. So these will be the number of ones in any subsegment. So if this value is greater than or equal to the value I need for any of those segments that I have from 1 to m here, right, then I can just return true for this particular value of mid. Otherwise, I will always return false. So at the end, I can always take at most q subsegments. If I was not able to find an answer among these q values and the value of h is still q plus 1, then my answer will be -1. Let me just explain you this a bit more clearly. So initially I assumed my answer is always going to be q plus 1, right? So this is a value at which my answer will definitely exist, and it might or might not exist at a smaller value, right? So if it exists at a smaller value, my value of h will update, and in that case my answer will be equal to h. Otherwise, if the value of h is still q plus 1, q plus 1 is not a valid value, because I can take at most q values from this particular array, right? So since q plus 1 is not a valid value, I'll print -1, otherwise I'll print the value of q. So this is how I can perform binary search, and let me just show you the code for this problem now. So what I've done is I've created a vector of pairs and I've taken input in it, and I have created a vector called set and I've taken input in it. So this is basically storing what are the indices that I have to set. I have initialized my low value with -1. That means this is always going to be false, and I have initialized my high value with q plus 1. That means I am assuming that this value is definitely going to be true. So I calculate my mid, and if check is returns true, that means it is a valid value for mid. Then I'll set my high is equals to mid, and I'll set my low is equals to mid. And at the end I check if high is equals to q plus 1. That means I have found no valid answer, and my answer will be -1 in that case. Otherwise I'll print high. So let me just show you the checker function. So what I've done is I've initialized a places array, and all of them are 0. So for all the places or all the indices that I have to set them as 1, I just mark them as 1. I'm taking the first mid values, and now what I do is I calculate the prefix sum for this particular array, right? Now I'm just traversing through all the subsegments that I had. I'm calculating the size of the subsegment, and I'm calculating what are the number of ones that I actually need in that particular subsegment, right? So this will be second value minus first value plus 1. And I divide it by 2 and add 1 to it. So this will be the number of ones I need. I can calculate the number of ones that are actually present in that particular range, and that is the second index places of prefix of second index minus prefix of first index minus 1. And if the value of current is greater than or equals to need, then I can just directly return true from here. Otherwise after all this loop is executed, I can return false. So this would be all about the binary search, and I've already explained what this value means. So this was all about today's problem discussion. I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video, and don't forget to share your thoughts in the comments, because your engagement with this particular video really helps the YouTube algorithm to understand that this video was actually helpful for you, and to be able to reach more number of people like you who want to keep solving new problems. So I see a lot of people who watch these videos have not subscribed yet. In case you are one of them, then do consider subscribing. It's always free of cost, and you can always unsubscribe later if you don't find the videos interesting. So till the next video drops, keep coding, stay safe, bye bye.